We'll talk about proving the logarithmic Kazhdan-Lusztig correspondence. Please.
Yes, thank you very much to you and all the organizers for inviting. I think this is a very nice way of bridging topics which are growing together or should grow together, and I'm very excited about it. So I promised to start slow, so let's at least say what we all agree on. So I'm from the algebra side, so for me, algebra and representation theory is a great tool to analyze symmetry. So symmetry is profoundly interesting, and I would go a little bit more precise in what I mean symmetry helps. So suppose I have a differential equation, and this has a group of symmetries. Then automatically the space of solution become a representation. So it's not like all solutions are symmetric, but if you have a solution and you apply your symmetry operation, you get another solution, right? Because the problem itself is symmetric. And I think that's the main point. So just to have an example that maybe is more familiar to you, you take eigenfunctions of the spherical Laplace operator, right? How can a sphere vibrate? Then you have an action of the group of rotations on the solution spaces. And you see that these solutions, here's a one-dimensional solution space, here's a three-dimensional one for different eigenvalues, you get different dimensional solution spaces. And these are representations of the group of rotations. And the point I want to make is that the representation theory here is very helpful. It can allow you to predict the dimensions of these spaces, the eigenvalues, even product rules. You take maybe a function here times a function here, and you can decompose them again into those functions. So this is what representation theory tells you in such an analytical problem. And I think this is great. And I do this in courses, so slightly graduate courses. I like to do this as an example a lot. So to be a little bit more precise, there is a Lie algebra hidden here behind the group of rotations. So yes, so the complex Lie algebra SO3 or SL2 acts here via operators, momentum operators. LZ is acting diagonally, so it acts by some scalar, here by 0, here by -1, here by -2. So this is the columns. And L plus and L minus are acting by lowering and raising operators. So this is how this is a representation of the Lie algebra SL2. And this is maybe the smallest example of a representation of a Lie algebra with a concrete analytic background. And then the Lie algebra somehow knows what kind of representations it allows. So there is exactly these type of representations, which look like chains. So L plus goes in this direction, L minus in this directions. And there are exactly simple representations of dimension 2L plus 1 for L some half integer. And you're seeing in the spherical harmonics exactly the odd dimensional ones, and the even dimensional ones would correspond to something like spin 1/2. So they are not here, but they are sort of there on the Lie algebra level. And you even have a tensor product theory. So if you take 2 copies of this representation and you tensor it, it's 9-dimensional. So there is 9 concrete functions as a basis. And it turns out this is exactly this plus this plus this. So these are these 9. So there's really a concrete product decomposition like you have for trigonometric functions. You can imagine this is trigonometric functions on the sphere, right? So, so this is sort of the kind of analysis I want you to have in the background when I'm now talking about representation theory. And always you can ask questions. So this was just the motivation. So let's now specify for this talk what kind of representation theory we mean and what kind of analysis problem we mean. So let's start with representation theory. And we have this in the previous talk by Chelsea. So a braided tensor category consists of what? It consists of certain objects, like these 2L plus 1 dimensional representations before, objects and morphisms between them. And our main interest is a list of simple objects, so the building blocks. And we want to know if all objects are semi-simple, so if all objects are direct sums of simples, like it was in the previous example, 1 plus 3 plus 5 plus 7, or if there's maybe some more complicated gluing between these guys going on. Then you have a tensor product rule and a unit object. So the unit object in the previous slide was the blue symmetric solution that we had at the top of the pyramid. And then you have a certain way of, you want this to be associative and commutative. But what does it mean? Associative does not mean that there's an equal sign, because these are vector spaces on the left and right side in our example. So you want some linear map between them, some isomorphism, which is compatible with all the structures you have. So it's not just a question of if it is associative, it's a choice of an associator, of a linear map between these and these spaces. And this is already quite non-trivial for the spherical harmonic case. And you want the braiding. So braiding means you want an isomorphism between X tensor Y and Y tensor X. And again, this can be just flipping tensor factors, but it also can be something more complicated. And it's called braiding because one of the axioms it should fulfill is if I switch u and v, and then I switch u and w, and then I switch w and v, it should be equal to the other way you can do it. So there is an equality between two different ways of using the commutativity law, and these two different proceedings should agree. So, but be careful that if you braid 2 times, so if I switch both sides and switch again, this may not be the identity. So for the spherical harmonics, this is the identity, but in general case, it might not be. So the braid group, the group of all braids appears. So this is sort of the basic structure. So we have, so for me, a good representation theory is that there's a notion of what is a representation, and there's a tensor product, and this is associative and commutative in a suitable sense. Is there questions already?
So the equality between these two diagrams is one of your axioms.
Yes, it's one of the axioms. Now it follows from other axioms, but you can, so it follows from the fact that this associator and this braiding has this hexagon equality, so they are compatible, and then you can somehow use this to cook up this. But you can also take it as an axiom if you want. So it should always be true. Let's say. So this is what I call a good representation theory. And the representation theory of the group of rotations we had is one example of this. So then much more easy example. So we have the following braided tensor category that will appear frequently. So it's vector spaces. So what are vector spaces? So the objects are finite dimensional vector spaces. Morphisms are linear maps. The objects are semi-simple. Why? Because every object can be written as a direct sum of one-dimensional vector spaces. I just taught this in linear algebra. So that's the existence of a basis, right? So this is what means semi-simple in this case. The only simple object you have is one-dimensional vector space, and you can write everything as a direct sum of one-dimensional vector spaces. And there is a tensor product that we learn a little bit later in linear algebra too. So one-dimensional tensor one-dimensional is one-dimensional. So n-dimensional tensor n-dimensional is n times n-dimensional. That's the tensor product. And the associator and the braiding are just trivial in a sense. It's exactly what you would write down. K tensor K is isomorphic to K tensor K. And now you can do the same thing a little bit enhanced with grading by a group, so let gamma be a finite abelian group. Let's look at the category of gamma graded vector spaces. Then, well, we have different simple objects, namely one-dimensional vector space decorated by a group element. So I always imagine these as vector spaces, but they're just decorated in some sense. Some subvector spaces are decorated by group elements. And the tensor product is a one-dimensional vector space with decoration A. Tensor, a two-dimensional vector space with decoration B, is again a one-dimensional vector space with decoration AB. And again, associator and braiding is just what you would do, namely nothing. So think about, right, the vector space of polynomials is graded by the degree of the polynomial. So this is the easiest example. So gamma would be here, maybe Z or N, maybe not finite, but it's maybe Z graded. So this is a common thing you have, right? Vector spaces with gradings. And now at this point we can enhance, because here we have made a choice, which is very natural. Just don't do anything. But we could also choose something different. So we could do the exactly same thing, gamma graded vector spaces, but as a braiding. So this is a one-dimensional vector space with degree AB, and this is a one-dimensional vector space with degree BA. And I could choose the identity morphism, which is just the matrix, right? It's a 1-by-1 matrix. But I could also put some number here, sigma of A comma B. And the same for the associator. I could put some number. And then my axioms tell me that there's a certain compatibility between these two things. And this gives me maybe the first example, and it will appear in the talk later on always, the first example of a real interesting, maybe not so interesting, but at least non-trivial braided tensor category. So it's gamma graded vector spaces, but if you switch to tensor factors into tensor products, or if you rebracket tensor products, you choose to have non-trivial scalars in the game that you just put in. And if you don't put them in, then it's also fine. But if you put them in, it's non-trivial. And in particular, if you now do this 2 times, nobody is promising that this has to be the identity. I mean, it's sigma AB times sigma BA. This is a product of 2 numbers. I mean, this doesn't have to be 1. So it is a real braiding, not just a symmetry. This may be the easiest example of what I have in mind for representation theory. But this is much easier than the group of rotation representations we had at the beginning. So there's other examples. So representations of a finite group G, and we take as a tensor product, just the tensor product of the vector spaces. And how do group elements act on the tensor product? Well, they act on the left and on the right factor simultaneously. That way you can tensor group representations. And again, as associated and braiding, you can just take the trivial maps that you would take from vector spaces. So you don't do anything fancy. And the same, of course, you can do not for a finite group, but for a Lie group or a Lie algebra. And this is the example in the beginning for the group of rotations or for the Lie algebra SL2. So let's recap. What we had in this case is we had for every number L, we had a simple representation of dimension 2L plus 1. And all possible representations were direct sums of those. And the tensor product had these funny rules. For example, 3 times 3 is 1 plus 3 plus 5. So this decomposes again into simples like this. So this is sort of the easiest example of what I consider a good representation. So this is the, now we want to have, of course, more complicated cases. Namely, the previous example, you can deform in a sense. So we have representations of the quantum group UQG. This means we take representations of the Lie algebra, like before, or the universal enveloping, but we deform, again, the associator and the braiding by a formal parameter Q. So basically, it's the same representation theory, but you fiddle Q everything. The same way before I fiddled in these numbers, sigma and omega. So I deform the structure. So it's still associative, but what linear isomorphism does the associativity has sort of changed. I fiddled in something with Qs. And this is already very interesting. It's Drinfeld's original motivation in the 90s, early 90s to define quantum groups because the monodromy of certain differential equations is measured by this. And you can cook up from this the Jones polynomial, not invariance, because, well, it depends on the braiding. So literally, this is no joke. It's when you write the knot as a braiding, which is closed up, and then you evaluate what it is. And you get some non-trivial numbers. And these numbers are sort of the Jones polynomial of this knot. So there is a very good, and Westermüller-Witten conformal field theory is based on this. So there's already this deformation of a known representation theory by a parameter Q is very sophisticated. And now let's go one step further. So if this Q is now not a generic parameter, but we take an L root of unity, then suddenly there is a non-semi-simple quotient, and we have a category which is non-semi-simple. So suddenly there can be more than direct sums of simples. These simples can be somehow glued together in a non-trivial way. And what this resembles vaguely is representations of this Lie algebra, but in characteristic L. So somehow when your dimension of your modules is close to the characteristic, so I said 1, 3, 5, 7, right? If it's characteristic 7, then something weird happens if the chain has length 7, because suddenly sort of 7 is equal to 0, and there's non-trivial possibilities to glue them together at the back and so on. So something weird can happen when you approach the characteristic of the ground field. And this is sort of closely related to this. And there's actually conjectures, some of them are solved, maybe not for this talk. And this is the representation theory I actually want to get at. So it has a non-trivial braiding, and it has a non-trivial way of gluing together simple objects. So also think about Jordan blocks, right? Usually you like every matrix to be diagonalizable. Now they are not. So this non-trivial extensions of simples is like, in the easiest case, like a Jordan block. So you have two simples, but they're somehow glued together in a non-trivial way, and it's the off-diagonal term. So this is the representation theory I have in mind. Now, what kind of analysis questions about this do I have in mind? Maybe spherical harmonics was a good call. It's a differential equation. Also here, there is a differential equation that's governed by this. But we want to talk about conformal field theory, and let's try to at least motivate a little bit what conformal field theory is. Maybe from my perspective, I'm more from algebra, but I try to, especially because we are people from very different areas, let's try to agree at least on some, maybe not agree, but let's try to put in some formulas that maybe you recognize. So for me, in my naive understanding, quantum field theory is something that builds on random functions, in a sense of you have a random field, and classically you take the one where the Lagrangian is minimal, so you want like the best field. There's one optimal solution, and that's the classical solution. But in the quantum world, you sort of average over all possible random fields, and some are more probable than others. Those who are more close to the classical solution of the differential equation are more probable than those who are very far away from it. That's maybe in a nutshell, and very naive, and probably people will so people in this room know conformal field theory better than me will probably disagree, but maybe that's the easiest slogan I can say. And the main output of the theory, which maybe we can agree all on, is correlation functions. So it's a correlation function says, what is the expectation value of this random field phi at a point z1 times this random field phi at a point z2, for example. So maybe if z1 and z2 are close together, then this is not the same as the product of the expectation values. If they are far away, it's maybe the product of the expectation values. And technically, on my side, I work with holomorphic parts of these conformal field theories. So not real valued functions, but complex functions which have monodromy and so on, like also in the talk of Evelyn. And also I just work in 2 dimensions. So it's 2-dimensional conformal field theory. And I use the language of vertex algebras for this. And the interesting thing from my perspective is that there is an associated representation theory. So giving such a very complicated theory based on these analytic functions, there is a representation theory associated to it. One of the types we had in the previous slides, and it's somehow expressing the analytic aspects of the correlation functions. For example, the braiding, switching to tensor factors has to do with the monodromy of these correlation functions, these chiral correlation functions, when you switch Z1 and Z2. So that's somehow what it does. And to connect maybe to other things that were said during this conference, let's maybe not make this more precise, but at least give one example where we can see this. So a scalar field is called free if you endow it with this Lagrangian. So you say basically a function is good if this quantity is small, and it's maybe bad if it's big. And this Lagrangian is then what we call free. And if you look classically, the one with the minimal expression here would be just a solution of this differential equation. So depending on your signature, maybe a wave equation, a potential equation or something. And in quantum field theory, it's a random thing. Maybe the 0-point functions are, the 1-point function is 0 by some symmetry, and the 2-point function is something like this, depending on the dimension. So it says the further the points are away, the less the correlation between the evaluation of these random functions at different points. And if you have higher correlation functions, then they're the product in all different ways you can decompose, the product of 2-point correlators. So this is also an aspect of being free. I mean, there's no higher interaction in some sense. It's just a product of terms like this. So this is maybe look and feel of a free field theory, sort of as much as I can for myself and for a talk, cook it down on a couple slides. So this is sort of the concrete output of a free field theory. And for arbitrary, not just R to the D, but for arbitrary Riemann surfaces or general manifolds, these correlators should transform under conformal maps or under conformal maps be 2-dimensional, but should somehow have a nice transformation behavior. And you can, for example, see that this is translation invariant in this case, right? It just depends on the distance. So this is sort of the output of such a quantum field theory. And now what we do in a 2-dimensional case, we identify R2 with C. And then when I said I want to go to the chiral conformal field theory, I'm basically decoupling this logarithm into logarithm of Z and logarithm of complex conjugate Z. And here this absolute value to the 1/2 is decoupled into this to the 1/2 and this complex conjugate to the 1/2. So you see I write everything as holomorphic and anti-holomorphic functions. And this makes my problem from R2 to a holomorphic problem and anti-holomorphic problem, but it's the cost of multi-valuedness. So suddenly these functions are multi-valued, and the braiding is exactly measuring this multi-valuedness. And now let's see very concretely how this then translates. So now if you look at 3-point correlators, they give a certain algebraic structure. So you can imagine this is a sort of multiplication rule. So A times B gives C with which coefficient? So for example, polynomials in this random field have just single valued correlators. For example, we saw this one. And this translates to a sort of multiplication rule. So it's if you have d phi, so the derivative of your random field times d phi is 1 with a certain coefficient, and the coefficient is z to the -2. And then there is other terms, of course. This is maybe the non-trivial content of this 3-point correlator. And if you now throw in other functions in phi, for example, e to the a phi, then there's also sort of a multiplication rule, and that comes from the fact, again, that you have such a correlation function. And this gives you here z to the -1 term, and this is again single valued. And that's what's called a module of this vertex algebra. So all of this is basically a kind of multiplication of things, but depending on z. So they are depending on what z1, z2, and z3 are. And if you now do this for 2 of these guys, you suddenly have a multi-valued function. So you have e to the a phi and e to the b phi, and then the correlator will contain something like z to the ab. And if a and b are not integers, then this is a multi-valued function. And so if this was too much, then I apologize. I just wanted to sort of arrive from the analysis side to what I want to say. So at the end here, the output really is for every number a, there is a representation. It's called VA. And the tensor product of VA tensor VB is VA plus B. And this we know, this is just graded vector spaces. And the braiding VA tensor VB goes to VB tensor VA is not the trivial choice. It's the choice e to the I pi AB, because here you have z to the AB. So literally the 3-point correlators tell you this tensor product rule, and the multi-valuedness of these functions tell you the braiding. So this is sort of the point maybe where I start, and but I wanted to try to go there because I know many of you work sort of more on this side of the correlators. So now I'm at the situation where I have associated to a conformal field theory. In this case, it's a free scalar field associated with a representation theory. It contains sort of large modules. The modules are sort of bunches of polynomials in these random field phi and its derivatives and its exponentials and so on. And they have a certain tensor product rule and they have a certain braiding. So for me, this always looks like representation theory of a commutative ring, but everything depends analytically on Z. So that's the statement I wanted to make, and sorry for the detour if this was confusing. So for a free field, which means like a random function of maybe the sphere or R2 to R, the main interesting cardinal correlation function is this. So it's a correlator, it's log Z minus W, it's a multi-valued function, and the associated representation theory is R graded vector spaces, R being the label of the exponential, and the braiding is e to the pi I lambda mu. And so that's sort of the picture I want to evoke is you have many different concrete models. You have these quantum field Lagrangians, you have stochastic models. I think in this case would be Goldstein boson or something. So you can make stochastically sense of what we did. And there's maybe many other models, but they all lead to a specific set of correlation functions. So it's called, what we call free boson. So this is mainly this correlation function that we had from the beginning now. And if we do the chiral part, then we have this vertex algebra, which has this multi-valued, maybe in this case it's single-valued, but in general it's multi-valued function. And this is now the holomorphic part of it. And this is what I'm interested in on one side. And the other side is you just have the representation theory. It consists of simple objects, VA, A, any label, any real number. And VA tensor VB is just VA plus B. So that's direct sums of these would be R graded vector spaces. And the tensor product has a braiding, but there's a non-trivial choice involved, which has to do with multi-valuedness of this logarithm. So this was maybe a long detour, but so this is somehow the picture I have in mind, and I'm talking about this arrow and how to invert this arrow more or less.
And the VA are Fock modules in conjecturalization.
VA are vertex modules, exactly.
Fock modules.
In this case, Fock modules.
Yes. But in the last step, they're just one-dimensional vector spaces.
Yes, I mean somehow it's the
okay.
same. From the category perspective, it's the same. But yes, so always things on this side have a lot more structure. Maybe that's things again. So that's sort of the message I want to put is here. It's just that here it's really trivial, right? It's just these labels, and maybe the scalar is the only non-trivial thing. What scalar the braiding produces. But here, this VA is not just a one-dimensional vector space. It's a big vector space. It contains all polynomials in d phi times e to the a phi. So many expressions in your random field, and that the tensor product is like this is highly non-trivial on this side. But the output somehow can be put in these. So it doesn't see a lot of the analysis, but it sees a little bit of it. It sees somehow this tensor product and it sees this multi-valuedness. That's the only thing the category retains. No. Right? That's somehow this arrow is why this arrow is drawn bigger than the other ones, because in some sense it's very non-injective, right? I mean, it forgets a lot of structure, all the analysis. And this is somehow the easiest case, right? What I said. So this is a free field. So now, what's called Kazhdan-Lusztig correspondence is there is more complicated West-to-Minowitten conformal field theory associated to a gauge group G, and the correlation functions have to do with this Creuzig-Logarithmic differential equation, and the associated representation theory in this case is quantum groups. So it's basically representations of the Lie algebra, but everything deformed by Q, and that's maybe why quantum groups were invented. And now the main question that for me is interesting is, can we also have these non-semi-simple versions, which have to do with specializing Q to a root of unity, where everything is non-semi-simple. So this theory, I think, is difficult enough and well studied for semi-simple theories, and I'm more interested in the non-semi-simple part. So, and there's works by Kutola and Peltola and others that we saw in the morning session. So for example, the crossing probability and some observables of critical percolation are a manifestation of a certain conformal field theory 2,3, which has some logarithmic singularities. And here again, there's many concrete models, maybe stochastic Löwen evolution should also be here, and they all lead to a certain set of correlation functions, which we call 2,3, W2,3. And if you now just look at the representation theory, there's a certain number of irreducibles. It's non-semi-simple. There's a certain tensor product, which is not so easy as in the last example. There is a braiding, measuring the multivaluedness of these functions. And this is a complicated object, this category. I mean, it's a complicated thing with many informations. And there is a different way of constructing it, namely from a quantum group at a certain third root of unity. And I'm lying a little bit because the quantum group, this would be rigid, as we saw in the recent talk. And this is not rigid. This is some sense of an extension of this by a minimal model, but maybe let me skip this detail. But more or less, there's a quantum group that also produces this as a representation theory. And that's maybe the two arrows I want to arrive at. So you have a certain bunch of correlation functions. You have an algebraic structure, which is a deformation of representations of SL2, and they both lead to the same representation theory. So that's the way I can understand, maybe not everything of W2,3, but at least the representation theory.
So what do you mean by that? Is the minimal model to free?
No, W23 is an extension of the minimal model. It contains the minimal model, but it's more.
A minimum model is trivial in this case.
Yes, exactly. In this case, it's 2,3 is trivial.
What is called is the logarithmic minimal model.
Yes, exactly. Exactly. Thanks. Logarithmic minimal model would be one way of saying it. Yes. So yes. So this is sort of the end of the second part. So basically, I come from this side. So I studied quantum groups, and later in Hamburg I was categorified. So I studied now with more categorical techniques, but I'm still sort of very much in this explicit. I mean, I like to have them also explicitly and check what they do. And now somehow one thing which is done a lot in Hamburg is that if you have things on this physics side and you want to see what their shadow in category theory is. And I want to do also the other way around. So I want to construct these objects from a very complicated representation theory. So put the analysis back in the picture. And that's maybe the point of the book. Yes?
Can I say that let's say the theory behind the Keter or Peltola should be even greater than the logarithmic minimal model.
It should be what?
Greater. I mean, like
yes.
It is not identified with.
No. This was more. So this is. I would say this is from this side. I mean, somehow getting from a certain stochastical or Löwen evolution model to this.
But
this is sort of this side, and I'm sort of working between these two.
Okay,
That's why I put the picture, so we are able to sort this out.
If you restrict to Virasoro, you have infinitely many primaries, infinitely many observables.
Yeah, I can do the same for Virasoro.
Extended symmetry, it's W algebra. If you take Virasoro part, if you restrict every of these certain irreducibles to Virasoro part, you get the whole cut stable.
yes, but like what I'm saying, maybe I'm saying that, for example, in percolation, you have like, for example, the connectivity probability that are not described by the W23.
I would have to look at this in detail. I'm not so familiar with but this is sort of very, very good questions, and that's why I'm in this conference. But this is stuff I have to learn. So for me, this is sort of this side, left side, right? I mean, what concrete things have to do with these correlation functions? But I'm interested in sort of giving these correlation functions from wherever they come. How can I construct them, or what parts can I see with representation?
Critical exponents of some observables in percolation. Some
Yeah,
observables
so
are there.
Some
He's not
claiming
claiming.
are there,
No, it's not a bijection. Yes.
some correlation functions are there, but
But not everything. No,
That's
exactly.
alive.
No, very good. Very nice.
Okay,
I mean, that's why we have a conference and
that's
not
why we are
a video
here.
recording.
Here.
Very good. yeah.
It's very complicated.
Exactly.
It's more complicated than
But let's keep these arrows in mind, right? Maybe this picture would be good to put on the wall, right? So this is this abstract, this conformal field theory in the sense of an abstract bunch of correlation functions. This is the representation theory, and this is an algebraic realization. And I want to go from this side to this. I want to construct analytic models for much more complicated quantum groups. Yes, so that's the picture I chose for this. So for me, there is sort of this big elephant in the room in the middle. So there is a quantum group, which is in this case for an arbitrary algebra G, and this is where I come from. There's sort of very complicated representation theory, and it produces this braided tensor category, which is non-semi-simple. And there is this conjecture, it's called logarithmic Kazhdan-Lusztig conjecture, because it's a non-semi-simple version of the affine algebra case, the W is a W module case. You have certain two-dimensional quantum field theories, conformal field theories, which conjecturally give the same. The representation theory is described by this. Those are very complicated models, and the WP, Q is like the SL2 case. So, and there should be for every G and even beyond. And that's what I want to talk about. So there's a list of contributions. So of course, most certainly Azad started all of this with Boris Feigin and collaborators. So this is a story since maybe 2006, or maybe correct my dates if I'm wrong. And then many people contributed to this. In the SL2 case, we're now finished. So there's two different proofs for SL2 after much work. And for general G, this is very recent work, and also many people contributed. And this is very recent work where we can prove the equivalence between this constructed conformal field theories and the quantum groups in general. That's sort of the content of the talk. And as you see, I mean, if you look at the SL2, you really see at the beginning they peak with the 4th unity case, and then people computed the simple modules, just the simple modules, no fusion rules. And then there is a tensor product and duality, and then people constructed, so Thomas Creuzig and Azad and Igor constructed a deformation of a sort of version of a quantum group, which is sort of more close to the answer, because this one is not quite right. You have to put associators. And this is sort of, you see how this really goes step by step. So this was a long process because the conformal field theory is a complicated thing. Let's now a little bit review how this goes from my today's perspective. So first of all, I'm just saying certain. So what is the conjecture? The conjecture is this side of the equality we get by taking the kernel of screening operators in a free field theory. So we start with a very easy free field theory, and we take certain operators that I will explain more. And the sub-theory somehow cut out by this is your candidate. And this somehow makes sense in this picture because the free field theory has representations, just gamma-graded vector spaces, so it's much easier than this one. And the gamma-graded vector spaces are representations just of the Kazhdan part of this quantum. So if you remember the initial example, there was LZ eigenvalues, this was the columns, and then there was lowering and raising operators that go left and right. And this is now just the graded vector spaces by LZ. So somehow there's still no L plus and L minus in. Those correspond to the free field modules. And then somehow if you take kernel of screening, somehow you're adding the L plus and L minus to the representation theory, making the representation theory much more complicated. That's somehow what happens.
So gamma is finite direct sum of cyclic groups.
In this case,
of the same, like.
Well, it depends on many things, but the gamma is something like the weight lattice of the Lie algebra, the dual weight lattice modulo P times the root lattice, and you have to be careful with taking the dual lattice because of stuff.
P is like a root of unity degree.
Yes. So something like this. So it's I would not say that it's always the direct sum of cyclics. I mean, of course, it's an abelian group. It is, but so it's some discriminant form associated to the weight lattice of this Lie algebra is scaled by some P's. Yes. But this is more or less. I mean, you could also imagine it's just weight spaces. I mean, it's vector spaces graded by weights of the Lie algebra. That's what you should keep in mind for vector.
Because of screening, they will cycle.
No, because of compactification, they will cycle. So because you're in a lattice vertex algebra and not a Heisenberg vertex algebra. If you do unrolled quantum group, then there would be no, it would be infinite.
You said you're just going to do the screening and
yeah, but that does not necessarily compactify this. It's just adds.
So in your example, gamma is infinite, right? R or R to the n for n free fields.
No, in my example, it's really what I said. But you could also do R to the n, and then you still can add your screens. It doesn't change this.
You're going to explain it, right?
Yes.
Okay. Sorry.
So yeah, it's vector gamma, and you should imagine this is either weight spaces, I mean, vector spaces graded by weights, or vector spaces graded by weights up to P multiples of the root lattice or something, depending on which quantum group you want exactly. And it's a little bit depending on your choices. Triplet algebra versus singlet algebra, and all of these things. Anyway, so the idea is to see how this is constructed, and that this has to do something with the quantum group. So it's like the LZ part in the SL2. It's like the Kazhdan part in the quantum group. And now maybe an important notion is to see that these screenings actually form a certain type of algebra, which we know from the quantum group side, which is called the Nichols algebra, which I'll explain. And this takes the role of the Borel, so just the L plus. So it's half what's missing for the Lie algebra, just the L plus. And then by some machinery, the L minus also pops up at something dual. But somehow you start to identify more and more stuff on the left side and the right side. And sort of when I realized this, so Alyosha Semikhatov had sort of some conjectures on this beyond quantum groups that this should be the Nichols algebra. And I proved this at some point, which I will show in a second. This is maybe the first time you see really systematically why the screenings here have something to do with the quantum group, because they just the same relations as the raising operators. That's maybe the part of the point. And once you have this picture, whether it's already approved at this point or not, I mean, of course, you have to do a lot of work, but you can immediately think about generalizations. And this is maybe even more important than what I want to say about the classical logarithmic Kazhdan-Lusztig correspondence. So the idea, and this is of course a little bit wild, but I think there is quite good evidence. The idea would be something like as follows. Start with any conformal field theory. And there's associated any braided tensor category. Let's call this Kazhdan. It replaces Kazhdan in the example we just had. Then I take screenings. They will generate some Nichols algebra. And let's call those Borel, just as a name. Then the kernel of screenings will be a more complicated quantum field theory. It will have a more complicated braided tensor category. And I say that we can define a quantum group on this side from these ingredients, which will be the corresponding analog on this side. So in some sense, this is much beyond an example class. It's more what happens if you take kernel of screenings. You're adding Borels. Somehow you're building a quantum group out of its Kazhdan part, and in a completely general case, in a more categorical sense. And that's what I want to say, actually. So that's maybe the main point of, maybe this slide is the main point of that talk. So this is what we want to do. And now I want to explain a little bit the ingredients and how we can prove this in this quantum group case at least.
So
yes?
that was Semikhatov.
Well, the Semikhatov, I think, was this kernel of screenings is the Nichols algebra, I think, but just for the quantum group case. I'm not sure if he would have gone to other cases, but maybe that was the intuition. Yeah, most certainly. So I mean, I learned this from Alyosha. So he came to a Nichols algebra conference talking about
free field theory, of course.
He just thought about free field theories, I think. So for him, it was just free field theory here, and he thought about this, but he wanted to go beyond quantum group, and he showed up at a Nichols algebra conference in Marburg, I remember, and gave a talk about conformal field theory, and I followed like maybe 10%, and but I was very intrigued by what he said, and so this started. And then I visited him in Moscow for a year, and so this is somehow. So that's what I'm saying. I think this idea with the Nichols algebra, I should attribute most certainly to Semikhatov, even though this is more on the level of diagram, so it was more like a pictorial. We expect this to be true, but you can prove it. Yes. So let's now try to make this picture more precise. Is there questions about this picture? Because I think that's the take-home message.
It's a nice picture.
This is you mean the elephant or the content? Yeah, because the point is you will see the elephant a couple of times more. It's like the quantum group has generous relations, but maybe it's not so visible. The point is actually this category in the middle, like from today's perspective.
Can you briefly remind what is screening?
Yeah, next slide.
Next slide.
So yes, so what is a Nichols algebra? And from my perspective, that's both a quantum group and a very categorical perspective. Maybe you not find this in books so easily. The Nichols algebra is something you can associate to any object in any braided tensor category. It's more or less like the exterior algebra or the symmetric algebras you associate to this, but because the braiding is not symmetric, double braiding is not trivial. It can be much more complicated. It can be the free algebra, or it can be some quotient. So it's in some sense the smallest Hopf algebra you can write down based on this braided object, in this braided tensor category. It's a very fundamental object. It appears in the classification of quantum groups and pointed Hopf algebras. That's where I come from initially in my PhD thesis. And it has, the funny thing is that even though it's extremely general, it has a certain root system theory, and you can classify it like Lie algebras.
That's for pointed.
No, that's in general. There is for example, over a Hopf, I mean, people here in this theory usually work just over another Hopf algebra because they are not doing this categorically. But there's theory by Andruskiewitsch-Schneider have a root system theory in more general cases than pointed. Most certainly. No, this is in general. This is much more interesting in general, actually. Pointed is just everything's one-dimensional, or the roots. So there is a certain, what I want to say is this B of X is a very universal object you can write down associated to any object in a braided tensor category. It's an extremely universal thing we have, and it's going to be somehow, you should imagine this as whenever you write down a Hopf algebra in a braided tensor category, this will be like the the nilpotent part. It like behaves like the universal nilpotent part that you can write down in this braided tensor category. And you have, for example, Borel parts of quantum groups, but you have also Lie super algebras, you have these Fomin-Kirillov algebras. Those are not pointed already again, right? This is over Sn. So there's other cases that are very interesting and studied. And the theorem that in this context I want to mention is, so suppose V is a free field theory. So I think this is true in more general cases, but prove I can just do it for free, just in this case. So V be a free field theory, like representations of the Heisenberg VOA, of lattice vertex algebra, whatever. Then the braided tensor category representations is these gamma graded vector spaces with some cocycles. And now consider screening operators. Then under suitable assumptions on the analysis, these screening operators exactly fulfill the relations of this Nichols algebra of the corresponding elements in this braided tensor category.
How they get X?
In general, huh?
How they get X?
Yes, X is basically just spanned by the screenings, exactly. And the nice thing about it, this works in any case, right? Whenever you have screenings, they live in some vertex algebra module. And there is a braided tensor category from the vertex algebra. So you always have this. This is a very general ingredient, but they are already very non-trivial in the easiest cases. And this is true. And
I think the question was, it's a Nichols algebra of what object?
Of the direct sum of these. So these are these screenings live in this vec gamma, right? So it's a direct sum of simple objects.
So you just consider them as
I
objects.
just consider them as objects in vec gamma.
Representations of VOA.
Yes. So the point is exactly. So if you think about Dotsenko-Fadeev integrals at the beginning, you use screenings from your vertex algebra. So they're from the unit object. But in this business, we always choose screenings that somehow point out of the vacuum module to other modules. So they have non-trivial braidings. And somehow that's what this theory measures. The non-trivial braidings because they are not part of the vacuum module.
Well, in physics, you usually like screen fields.
Maybe something like
Yeah,
this.
but
Yes.
that is supposed to be
So,
morphisms.
yes. So, just to give you again, because I'm talking with people who like correlation functions and analysis, maybe for me this is further away, but let me say what this theorem amounts to in the easiest case. So maybe you recognize something. I'm just, if it's confusing, just ignore the next slide. I just want to give the example. So what it actually means is the following notion. So suppose I have some complex numbers mi and mij. Then I look at the n-fold contour integral of this function. So this has some singularities that if zi is equal to zj, and you have to lift it to a cover, of course, because it's multi-valued functions, because mij and mi are complex and maybe not integers. Even half would be interesting, right? And then this integral converges under certain condition, which you can write down, which is maybe not so interesting. And now the assertion amounts to, if you really write it down on the analysis side, it amounts to proving that a certain linear combinations of these f's is zero. So there's linear dependency between these integrals, exactly if the Nichols algebra says it should be zero. And which Nichols algebra? Well, the one where the braiding is e to the pi I mij, and mij is exactly this mij. So it really measures exactly this. So the point is, when you write down this integral for the first time, you think, well, if I switch zi and zj, nothing happens. Then you say, no, but maybe a minus sign happens, but it's to the mij, so maybe e to the I pi mij happens. But that's not true, because this contour. So this would be the trivial case. So this is not true. If you switch zi and zj, much more happens than just e to the I pi mij. But if there is a certain dependency between these mij's in a non-trivial way, then there's still some dependency between these integrals. And that's exactly what the Nichols algebra measures. So in the easiest case, it's Q commutative. That's when you just pull in front e to the I pi mij. But in the general case, it's a free algebra, so there's no dependency. But sometimes if there's coincidences between these mij's, then there is some relation. So that's what the Nichols algebra measures. Yes. And the proof is basically you decompose this integration domain into n factorial simplices, and then you transport them back and you get some quantum symmetrizer, and I'm not going to go into this. And yeah.
Can you set another point? Can you do this analysis by adding ZD minus 1? Can you?
Well, of course, you can always add Zi minus 1 because I can rescale one of the ZJs. I mean, this is for every number of insertions. Right, you can just insert one and set it to 1 or rescale.
Okay.
Of course. So this is the quantities, and I think we had them also in the talk I mean, maybe not these integrals, but these are exactly the Dotsenko-Fadeev integrals, right? I mean, this is no surprise, of course. But the point is now, also compared to the talk in the morning, now this statement holds in principle for all values of mi, mij, and so on. But in general, the answer is simply that there is no relation. But now if there is certain fractions here, or if there are certain dependencies, suddenly you get some relation. So it matters exactly what happens if this is not generic numbers, but there is some sort of integrality conspiracy between them. And this happens for generic quantum group as well as even more for a small quantum group.
So you find the dimension of the space spanned by this conformal block.
Yes, this is not really conformal blocks, but this is more like the structure coefficients of screenings. If you multiply two screenings, then you get these factors because you have to write out hypergeometric series, and that's what you get. So this is, I think this is closely related to the hypergeometric function you get in critical percolation. It's a crossing probability. This is also an integral like this. I would think that this is the same, but so this is somehow, again, I'm saying much more analysis than I would usually do because this is maybe what people recognize. So this is what screening means. And to be even more explicit, let's look what happens in degree 2. So in degree 2, I can compute this integral. It has some e to the 2 pi I m2 and so on. So there is some integrality things. And then there is Euler beta function.
So what's degree 2? It's just two
insertions. Two
dimensional.
Two insertions. So there's two variables, Z1 and Z2. So I integrate, so here.
Dimensional x, right? That would be like
Z1 and Z2.
Two-dimensional v.
N equals 2. Yes, exactly, the same as dimension v. And now what you see is, here is like some complicated, I mean, in this case, you can even work it out. And in general, it will be some hypergeometric function. It will be some combination of beta functions. But the point is, you can write this f using complex analysis into some other f plus e to the pi I m12 times some other f, some combination of these things. And now we see two types of Nichols algebra relations appearing. For example, if m12 is an integer, then this sign m1 and this sign m1 are either equal or equal up to a sign. So it means that this expression is either the same as the expression when you switch m1 and m2, or it's minus this expression. So either you have, it's like, and you have a relation like this. And this is the easiest Nichols algebra relation. So x1, x2 is the same as plus or minus x2, x1. It's a commutator or anti-commutator. So I said it's an exterior or a symmetric algebra. So you see really on the analysis side here, this relation between these two integrals. Or if m12 is an odd integer, then these two beta functions and m1 is equal to m2, these two beta functions cancel. And this means some square is 0. And this is again in the exterior algebra, you see the square is 0. And you have to be careful if this formula has some poles. And in this case, you see interesting things. You see extensions of Nichols algebras, but maybe I'm not talking about this. But sort of there is analysis hidden here that goes beyond Nichols algebras. But in the cases that we look at in this talk, maybe this is not happening. But anyway. So this is very explicitly what happens on this screening side. So, and now the theorem I want to present is sort of the free field version of the general picture I presented. So the theorem is as follows, it's from this spring. Let V be a free field theory. For example, lattice vertex algebra or Heisenberg vertex algebra. And its braided tensor category of representations is of course vect gamma omega sigma. And now let's take a kernel of screening operators. Then I have to assume something in the analysis, some convergence conditions, but then the following holds. The braided tensor category of representations of W is equivalent to what? Well, we take the Nichols algebra generated by these screenings. This is a certain algebra. It can be a free algebra, or it can be a quantum group Borel part, or something more complicated, quantum supergroup Borel part. Inside this category, it's like the L plus, if you remember the picture from the beginning, and here's the LZs. And of this is not braided, has no braiding, but of this we take the relative Drinfeld center. In a way defined by Logarithmic and Chelsea. Of course, this was there before, but I think their reference is the best to how to construct really braided tensor categories out of tensor categories which contain a braided tensor category. So it's some relative version of a Drinfeld double on the algebra side. But so it doesn't maybe matter. It's like a way of putting the dual, the lowering operators also in the game. So this way it constructs a braided tensor category and it proves that those are equal. Careful, I have to assume that the analysis is nice enough. So this is what other people work on, like Thomas Creuzig and Jinwei Yang and Robert McRae and So you have to even prove that the vertex algebra representation category is nice enough to have a tensor product. And these things I have to assume. So for SL2, we know this by some work, but in general, we don't know this. So in this sense, it's conditional because I cannot solve this analysis problem in this generality, of course. But somehow it's a recognition theory. Like this defines you a very good candidate, and it says if this is a tensor category at all, it has to be this one. And this explains why it has to be this one. Yeah.
Terms in the previous slide terms, it will be like conditions on MIJ.
It will be, well, it will be conditions on MIJ, but it will be much more. It will be the fact that you even have a tensor product of the vertex algebra.
Yeah,
this
so
is C2 cofinite, for example.
But yeah, in terms of MIJ, it will be still a condition.
Conjecturally, it only depends on the MIJs, but I could not prove this. I mean, proving C2 cofiniteness of a vertex algebra is a very different type of problem.
But do you have a conjectural bounds, like when it happens?
I think exactly when the Nichols algebra is finite dimensional. And this depends very much on the MIJs.
Finite dimension.
Yes, I think so. Because I mean, if you believe if you believe this, then the categorical dimension will be exactly the square of the Nichols algebra dimension. So it gives you a bound.
Why finite dimensional? You still have ordinary Kazhdan-Lusztig.
Yeah.
And there it is not finite dimensional, but you still have a Kazhdan-Lusztig correspondence.
Yes, because this corresponds to a Nichols algebra, which is infinite dimensional, but in a very controlled way. So for example, it has a finite Gelfand-Kirchhoff dimension. So it's the Borel part of a generic quantum group,
Yes,
right?
yes.
Not finite. So in this case, it's still finite in
It still
some
works.
sense,
It's still tensor.
Yeah.
Yeah, tensor category.
Yeah. So of course.
Yeah, maybe later.
Okay. Yeah. So,
But
so this is
category here, they're rigid, right? Relative Greenfield center is rigid.
yes. In this case, it's rigid.
So here it's all rigid, right?
Here it's all rigid.
So it doesn't cover W23.
No, for
Why
W2.
does not?
So for W23, this is not a technical question, but so for W23, what happens is you still have the free field theory as an algebra,
Yes.
and you can induce up, but the induction functor will not be faithful.
Uh-huh.
So the point is, in this case, you will, if this is
You
not
construct some
rigid,
quantum group, right?
you construct a quantum group that somehow the image under
Yeah,
this
yeah, yeah.
induction
Okay.
functor. So this means you forget some modules, but you see the rest, right? This is exactly what you were think about a lot of times. So, but I think this observation, and I think I know from you, this observation that there is a quantum group, but it's not, it's like a quotient of the category.
Yes,
I think
yes,
it proves exactly the quotient has to be like this.
Yeah,
It doesn't say anything about the kernel because the kernel is annihilated by the.
But can you prove that it's a quotient? Because in WPQ you
Yes, I
have
can. This is part of this
ideal
result.
minimal model forms a tensor ideal,
Yes.
and then you can take quotient. Can you
So-
prove that it will be this?
Yes. In fact, I can prove stronger. So what I can prove is the image of the induction functor with the free field algebra will be exactly the quantum group.
Ah,
So it's not just a quotient; it is precisely the stuff that's not annihilated by the free field algebra.
I see. So you construct only subcategory.
Yes.
Subcategory. I see.
So, yes. So the idea of the proof is basically as follows. So it's like a recognition theory. I mean, you have a complicated category and you don't know much about it, but you have to recognize it. So the idea is the free field algebra is a commutative algebra over the smaller one. So this is the complicated one. This is the free field algebra. And what we do with Thomas Creuzig and Matthew Rupert is we develop general tools to reconstruct the complicated algebra from the easy one, which seems like you pull an elephant out of a hat, right? I mean, the elephant is complicated, but I put in just a free field algebra. How should this work? Well, you have to add a little bit more information. You have to add information about the x1s, and those tell you which Nichols algebra to take. But somehow the theorem is like, suppose you have sort of any category where this is a commutative algebra and I know the modules over this, then I can reconstruct this category as a Drinfeld center of some Nichols algebra. That's somehow the algebraically the result. So it's a reconstruction.
So can I ask?
Yeah.
So W is a vertex.
Yeah.
Algebra. Vertex subalgebra of B.
Yeah.
But isn't vertex operator subalgebra?
Yeah.
It's a kernel, right?
Yeah. It's like triplet algebra inside free lattice algebra or singlet inside Heisenberg.
So that is like Kirillov von Lipovsky type.
Yes.
Yeah, he's
Local
doing
model.
this. Yes, he's doing this.
Exactly. But the point is to reconstruct the algebra from the local module.
Yeah.
So this is the other way around.
Yeah.
And I'm telling that in general, there is an x1, and this tells you which Nichols algebra gets added, and that's the result. So if you want, it's also a way of having orbifold theory, but not for groups, but for Nichols algebra.
Yeah, but yeah, like
That's how I would think about it. It's an orbifold theory.
Runkel sort of type of.
Yes, exactly. But not for groups.
Yeah, Cargill-Runkel.
Yes.
Yeah, just.
And those are braided, that's the point. The braiding comes in. So this is how we pull the elephant out of the hat. And yes, so as some writers said, as soon as the wish is fulfilled, it gets many children. So we have this result now. So this is interesting maybe from several perspectives, but first of all, I would like to prove the statements that we had before, not just in free field theory. And in principle, I think this is possible. So the technology is more or less there. The point is for free field theory, I can write down these Stotsenko type integrals and just check. In general, I have to use the whole machinery of Wang, Lipovsky, Zhang. Says you have some differential equation with some regular points, and this is the only information I'm allowed to use. And in principle, it's enough. It's exactly the information I need. But it's a very different type of proof. It's much less explicit. So, but I think it's true, and I would very much like to prove it. Then one question you can ask is, you have these braided tensor categories that arise from semi-simple ones by adding Nichols algebras. Are these all? I think so far we have not seen a counterexample. It could be that really all non-semi-simple tensor categories arise this way, or not, and then I would like to see a counterexample. So both would be interesting. I'm not even sure what I would conjecture. So this tells you it's not about constructing examples. It's more about like understanding in general what happens when you add a non-semi-simple part to a tensor category, or if you go to a kernel of strings. And then we work on cases beyond the quantum group. So for example, with Thomas Creuzig at the moment, we work on the super algebras and on Lie algebras at admissible level. So for example, SL2 at certain admissible level looks like certain quantum group at SL2/1 with some semi-simplification going on. So these all you can prove in a similar way using these reconstruction results. And something I'm very interested in recently is with Boris Feigin. There's a couple of, I think 3 papers out. You can deform this by a flat G connection. So G acts, the Lie group G acts on this whole thing, and you can deform by this. So I think on the that's why I ask in the break. So you can, I think also these SLE types of things, I think, I have no clue about this, but so people always said we use sort of trivial choices of what you use as differential or something. You could distort this by something. So you can have maybe a 3-punctured sphere, but it's not just a 3-punctured sphere with a trivial connection on it. So D, but you put D plus A for some potential A. And then it deforms your definition of conformal blocks, and this is something Jörg Teschner knows much more about this than me. But so you get sort of more structure. It's deformations of what we had before. And again, these we can describe by quantum groups, at least to the point where we understand it now. And there are certain connections to quantum geometric Langlands kernels. So basically, if you take limits of those, then you get the respective deformations.
So in this G for you, it's a billion.
No,
you have a billion or
Lie group like SL2. Take SL2. So this is something I'm very interested in at the moment, and you can even deform by stuff which has irregular connections, then it's even more interesting. Maybe there's one paper.
Do you understand the category for it? Do you understand the category?
Whittaker modules. It's Whittaker modules of the singlet algebra.
No, quantum group level.
No, on the quantum group level, I don't.
Oh.
That's one thing I thought about in the plane. So this is the moment what we try to find. So it has something to do with Kazhdan-Lusztig quantum group, but
yes,
what exactly I don't know.
No, it's more interesting.
Yeah, more interesting. Yeah, so this is more or less it, and maybe my time is also over. So I have prepared some slides more on how more technical these recognition theorems look like. So in principle, what we have is, for example, you have this standard statement that if you have a category with a fiber functor to vector spaces, then this category can be reconstructed as a category of representations of some Hopf algebra, and we need some relative versions. So you have 2 different categories and a fiber functor between them. Then you can, if there's a splitting, then you can reconstruct one as representations of a braided Hopf algebra. That's part of, and another part is if you have category of local modules, then you can reconstruct the category as Drinfeld center of your Nichols algebra. And that's, I think, an important result in general. I mean, it just tells you how to revert the process of going to local modules. But this is maybe more specialized enough for this module. So maybe that's a good point to stop.
Okay, questions?
This last deformation that you mentioned, is that deformation then by operas?
Yes. I mean, you can do it by operas or by connections, right? I mean, there is a Hamiltonian reduction between these 2 notions. So both works. I mean, the standard example you have in mind probably is affine Lie algebra at critical level. Yeah. And that's exactly one thing you get. But in general, So if you have an action of a Lie algebra G, then what you expect is a deformation by G connections. And then after Hamiltonian reduction, you get something with opers. But before, actually, this is the more sort of bigger, more natural object, at least in this context.
Do you need something like a big center in some
We
algebra?
construct this. So we construct, so you can either start by this Langlands kernel, then you put some parameter to infinity, and then you get a vertex algebra with a big center. So you get this out of this very complicated objects, which I understand only a little bit, but you can construct from this a big vertex algebra with a big center, or you can take your initial, that's the most recent paper, you can take a vertex algebra with a G action and somehow couple it with a very big center and construct sort of by construction a vertex algebra with a big center. And correspondingly on the quantum group side, you expect, of course, a quantum group with a big center where sort of the fiber over 0 is the small quantum group and the other fibers. And for regular singular, this works, and for irregular, it's more interesting. So, yes. Yeah.
Maybe exactly about this, just to become a bit more concrete. So the limit of these quantum geometric Langlands, where it develops a big center, is this then some extension of a fine Katz-Moody rather than W algebra? So for example, if triplet is extension of Virasoro, but it has some relatives where Virasoro is replaced by the corresponding sort of, inverse Drin-Sokolov.
You're very right. But both exist, and actually all four combinations exist. So when you take this quantum geometric Langlands kernel per se, and you go to this limit, then it has a big center, which is G connections, and the fiber is somehow, as I say, the affine cousin of triplet. But now you can do on either side of this construction a reduction, and then you're maybe fibering over opers, but your fiber is still this affine guy, or you're fibering over G connections, and your fiber is triplet. Or you're fibering over opers and your fibers too. So, but all four combinations exist, yes. And the point why I think it's difficult to work with the guys before reduction is because for these we tend to have no models, in the sense of there is no vertex algebras that appear otherwhere in nature that I can use. I mean, these things you can write down as a direct sum of products, but you cannot. There's no model for it. And for the reductions, there is often something like. Yeah, maybe that's too specialized, but I mean, you can a little bit work with it more explicitly. But all of these four combinations are, of course, there. Yes.
I have one question. So you expect all modular tensor categories appear this way. If it happens that it's G-graded modular category, you can do naive thing. You can change braided structure by third abelian cocycle. Do you understand what it does on the level of UA?
It will change the VOA very much. I think it's not doing anything on the VOA side. It will not be a simple operation on the VOA side because it changes, for example, ribbon structure extremely. So, so I think you should rather think about it as follows. So, I don't claim I understand all modular tensor categories. It would be a little bit much. The point is more start with a semi-simple one, then I claim we can understand how to add the non-semi-simple part. And what you're saying is just happening on a semi-simple part. So the idea is more that you have like a square. So you have maybe one VOA, semi-simple with a G-graded extension, a VOA with the other G-graded extension. And now for both, you can take kernels of screenings. And then you get sort of quantum groups where the underlying semi-simple category has a different associator. So it's more like your Kazhdan part would be different at the start. It's maybe that the question. So
maybe.
I think it's orthogonal to the construction. So you're changing the semi-simple part.
Yes. Simple part is changing. Yes, what I'm saying, simple part is also changing.
Yes. So somehow it's 2 times the same quantum group, but with slightly different Kazhdan part. But there is no, I think there is no bridge between. I mean, you see this from lattice VUAs even, right? I mean, if you have the lattice VUA and you have two different Z2 graded extensions, then they have to start with different ranked lattices. I mean, they are completely not related.
I mean, maybe the other question is, if I give you Kazhdan part, whatever it means, can you reconstruct the VUA? No.
I mean, that would be, so I think exactly,
that's the point.
I'm stating exactly the opposite, right? I'm saying if for the Kazhdan part, you give me a VUA, then I can give you a kernel of screenings for the quantum group. So it's sort of, if you give me for the semi-simple what you want, then I can sort of add the Borel parts. That's the.
Okay. Conjecturally, we're just saying that all finite modular tensor categories come from Nichols algebras in semi-simple.
In some semi-simple, yes. And you can reformulate this in a sense of is there in every Witt equivalence class a semi-simple modular tensor category?
Yeah.
That's the
my
question, exactly. And I think this question is difficult and maybe people study it and I think there's no answer, but I talked to
We lack examples. Yes.
Yes.
Maybe for a reason because they don't exist.
Yeah.
Or maybe, yeah.
I'm not sure. I mean, I'm not saying it is. It's more like I've not seen a counterexample. And because the nice thing, if this would be true, or even if it's not true, but for those, we would have a uniform construction of the corresponding vertex algebras. Suppose you have for the semi-simple one.
Okay, there might not be even vertex algebra behind them, right?
Yeah,
But sure.
exactly. For example.
Like any finite tensor modulus.
Yeah.
Logarian will have a fiber function to some simple.
Fine. I'll be curious to see example, counterexample, or proof. I talked to Nichols about this, and he curious question.
Good. Seems no more questions. Thank you, Simon, again.